Okay, here's a fact. Suppose we have a composition of functions f and g, and let's suppose that we're evaluating a limit where the inside function g is going to plus or minus infinity. Well, we can replace this limit with, it doesn't make sense for me to plug in plus or minus infinity into f of x. Instead, I can rewrite this limit as the limit of x going to plus or minus infinity of f of x. Namely, I'm replacing g of x with a parameter x that is tending towards plus or minus infinity depending upon what g is doing. So as an example, let's evaluate the limit as x goes to 0 from the right of arctangent of 1 over x. Well, I know that 1 over x approaches infinity as x approaches 0 from the right. Well, it doesn't make sense for me to write down arctangent of infinity, but what I can do is, since the limit of 1 over x is infinity, I'll replace 1 over x with x and let x tend to infinity. Well, the limit of that is pi over 2, so our original limit is pi over 2. Okay, similarly, let's do the limit as x approaches pi over 2 of e to the tangent of x. Well, as x approaches pi over 2 from the right, tangent of x approaches negative infinity. It doesn't make sense for me to write down e to the negative infinity. However, since tangent is going to negative infinity, I can replace tangent with a parameter x that is going to negative infinity. So our original limit is the same as the limit as x goes to negative infinity of e to the x, and we've already said that that is equal to 0. Now we can also have infinite limits at infinity. So I will say that the limit of f of x as x approaches infinity is infinity if we can make the values of f of x as big as we like by taking x big enough. So as x gets bigger and bigger, f of x gets bigger and bigger without bound. Okay. And we write this as the limit as x goes to infinity of f of x is infinity. We have similar notions for f of x going to negative infinity and for x going to negative infinity. Graphically, these four different possibilities are represented by this. If I have a function that goes to infinity, as x goes to infinity, I represent that by an arrow pointing up and to the right. X is getting bigger and y is getting bigger. If I have an infinite limit at negative infinity, that's an arrow pointing up and to the left. As x goes to negative infinity, y is going to infinity. If I have a negative infinite limit at infinity, exemplified here by the limit as x goes to infinity of g of x is negative infinity, that'll be an arrow pointing down and to the right. As x gets bigger, y is going down to negative infinity. Finally, the limit of g of x is negative infinity as x goes to negative infinity is exemplified this way. As x goes to negative infinity, g of x is going down to negative infinity. So these arrows are supposed to mean these four different limits. Okay, so the most basic functions we have are polynomials. And we can always write these as f of x is equal to a times x to the n plus lower degree terms that have a smaller power than n. Here a is called the leading coefficient and n is the degree of the polynomial. What happens at plus or minus infinity depends only on whether a, the leading coefficient, is positive or negative, and on whether n, the degree, is even or odd. If the degree is even and the leading coefficient is positive, then the function goes up on both ends. That is to say that the limit at both infinity and negative infinity is infinity, positive infinity. If a is negative and n is even, then both ends go down. As we go to negative infinity or infinity, the values of the function approach negative infinity. When the degree is odd, the end behavior is opposite on each end. If the leading term is positive, then it starts down to the left and goes up to the right. So the limit as x goes to negative infinity is negative infinity. The limit as x goes to infinity is infinity. If the leading coefficient is negative, then it starts up and ends down. So the limit as x goes to negative infinity is positive infinity. The limit as x goes to infinity is negative infinity. I like to call these happy, sad, up, down. Okay, so now this allows us to deal with rational functions where the degree on top is actually bigger than the degree on the bottom. So let's look at the limit as x goes to infinity of 3x cubed plus 1 over 2x squared minus x. I'm going to do the same thing that I did before. I'm going to identify the highest power on the bottom, and I'm going to divide everybody on top and on bottom by that power. So the biggest power on the bottom is x squared. Divide everybody by x squared to get this expression. I simplify to get 3x plus 1 over x squared over 2 minus 1 over x squared. Now the top is not a constant in this case. It begins with a polynomial. So I can use the facts about polynomials to determine what's happening on top. 3x, well, the leading coefficient is 3, so it's positive. The degree is 1, so it's odd. So the top is going to infinity plus 0 is going to infinity. The bottom, well, 2 is 2, and 1 over x squared goes to 0, so the bottom is going to 2 minus 0 is 2. So I've got a quantity going to infinity divided by a quantity going to a positive constant. Infinity over a positive constant will give me infinity. Okay, question 3. Evaluate the limit as x goes to negative infinity of 3x cubed plus 1 over 2x squared minus x. It's the same problem as before, but instead of having x go to infinity, I'm letting x go to negative infinity. Now just to finish off, let me mention that there are just two common infinite limits at infinity that we should know. First, the exponential function. As x goes to infinity, e to the x goes to infinity. That's exemplified by the fact that this exponential graph, as x goes to infinity, just shoots off the graph. Great. Also, the natural log, as x goes to infinity, also goes to infinity. Now this graph sort of curves down, and if you went out really far along the graph, it would look almost like it's flat. The thing is, it does get to infinity. It gets there really slowly, but it eventually gets there. So this graph also has y going to infinity as x goes to infinity.